So let me share my screen. Stop. Present. So in the year 2000s, right, unsupervised machine learning techniques became very widespread. And that's because if we have data and we do not have labels, what are we going to use with those data? So techniques on how to actually, understand what this data is actually meant for started in the year 2000s. And there is this favorite quote that I like by Ian Lincoln that states, if intelligence was a cake, unsupervised learning would be the cake, supervised would be the icing on the cake, and reinforcement would be the cherry on the cake. So I love cakes a lot, and I love quality sweetened cakes. However, before I take my cake, I always remove the icing and the cherry on the cake so I can, have that yummy feeling and have that yummy taste. So Yanikon is trying to tell us here that if you, rather than focusing on other extra stuff, let's actually focus on the data. That's the actual stuff. That's the cake.
So I mean, that's a great analogy, but you should not eat too much cake in the US. I told you, you're gonna grow big. We won't recognize you. Okay. So you have to be careful. And then number two is so he's gotten into trouble. Jan LeCun is like head big giant of AI at Facebook. So people like Sina may not know who he is, but so big name, he would be like, the big giants of interventional radiology when we hear about them. And he's gotten into trouble with his data statements, right? So he's very data centric, and he's gotten into trouble by saying data not biased, and there are all these things online that usually happen when he says those words. So that's it. That's my interruption.
Okay, thank you, Dr. Chite. So why should we use unsupervised learning? So there is huge potential in unsupervised learning, because we have like lots of data that do not have label, and also because it is very close to human intelligence, right? That means unsupervised learning is actually very close to human cognitive functions, just like the human brain. It deduces patterns, right, and slowly learns about the world in time. So I decided to, think of a practical example of unsupervised learning, and this time I didn't want to consider medical examples. I wanted to consider something natural to my territory. So this was my field attempt of coming up with an example in 30 seconds. So I have a colored printed page, and I make a grayscale and a full color copy of the printed page. Now these papers are mixed and shuffled somewhere, and the goal is to take a picture of the printed page, and the phone automatically predicts where to fall, maybe a grayscale copy or a full color copy. Now, mind you, the phone doesn't understand black and white or full color copy because there are no labels in the data. It identifies these two classes and groups them based on some kind of similarity. So after my field attempt, I tried to check the text, see what they have there. So they had like really exciting examples, better than mine. So I checked two textbooks. The first I checked was Hands-on Machine Learning. That's the book we are currently reviewing. And there are some examples like a system takes pictures of items in a production line to detect which items are defective. Having a CCTV camera installed can actually take lots of pictures of different items daily. And you can always set up the camera and make sure that the pictures that are being taken are actually different from the previous day. And also an algorithm looks through this data, detects similarity between them, and classifies them based on such similarity. Then I checked another textbook, that's the Dive into Deep Learning by Mark Gardner et al. And rather than giving examples alone, the authors of these textbooks actually proceeded to asking questions. Now, the first talks about clustering. So if you have a large collection of user browsing data, can you group them into users with similar behavior? Now, this is known as clustering in supervised learning, and customer segmentation is a good example of clustering, which involves grouping users with similar behaviors based on a large collection of browsing data. Then the next example with question is, can you capture the most relevant amount of data, parts of large amounts of data, and this is known as principal component analysis in unsupervised learning. So a very good example of this is tailors have actually mastered this by knowing where to measure when sewing clothes. So they know that if they measure your length or probably your waist or your hand, they can actually accurately sew and describe the clothes that fits. So this is so problems like this are regarded to as sub-estimation problems. And when the dependence is linear, then it's known as principal component analysis. Now, another one is representation learning. So objects in a Euclidean space, such as properties of an object, can actually be matched, can actually be well matched. So for instance, let's say you are going to Paris and you have Rome, Italy, and France as features of the data set. So if you know that Rome minus Italy plus France equals to Paris, so you can probably just make use of Paris in your data set when analyzing it. So I think let me see. I think what actually happens is when you combine features, you can actually get another feature. So that what happens in representation learning. So the next question that was asked here is, I have a human population data that contains information about house prices, pollution, crime, location, education, salaries. Can we actually determine the relationship between these features, right? So when you try determining the relationship between all of these features, this is known as causality and probabilistic models, and it addresses this concern.
Just
So
one second, go back to that. I mean, this is really good. What was this book again?
dive into deep learning.
What?
Dive into deep learning.
Dive into deep learning. I mean, that's pretty good. Does it approach like everything in this question format?
Yes, it does.
Oh, wow. So, causality uh, is interesting, in my opinion, because this is something that I personally do not know, but it's a big thing for just interpreting machine learning, and is something that we should try and get some book or something to go through in future. I just wanted to put that. So this is pretty good.
Okay, thank you.
Mhm.
So we've defined clustering. An example is customer segmentation. Now for anomaly detection, you learn what normal looks like and what abnormal looks like. So you can easily detect abnormality. And then for density estimation, you have low density and high density. And this is very good for data visualization and analysis. Now, some clustering applications, customer segmentation, we mentioned that data analysis, dimensionality reduction, anomaly detection, and for search engines. So there are two popular clustering algorithms, that's the K-means and the DBSCAN. And this is the K-means. The K-means is a very fast algorithm because it's linear, and the K in K-means algorithm means clusters. So if you consider the unlabeled data sets here, you can clearly see that we have blobs of instances. So clusters here are referred to as blobs of instances. So we can see 1, 2, 3, 4, 5. It's so obvious. And the next slide. So how can we now use K-means? So the first thing that we need to bear in mind is we need to specify the number of clusters. So in this case, we have 5 clusters. We create an object of the class or an instance of the K-means class and insert the number K, which is done here as the number of clusters. And then we make our prediction using the fit predict function. So the things that we need to note when you're making use of K-means, so you have to specify the number of clusters, you find the blob center, and assign instances closer to the blob. So blob means clusters, right? And if you have 5 clusters, in order to find the center of the cluster, you take the mean of the instances in that particular blob or cluster, and the instance label is the index of the cluster, compared to a classification where you have like a label, right? In this case, there is no label. So when you have different clusters, the index of that cluster 0, 1, 2 is the label of the cluster, and instances are assigned to one of the 5 clusters. So when you have the 5, it looks like it looks at the one closest to the centroid or the mean of the instances in a particular cluster, and then it assigns that instance to that cluster. Yeah, so we can take a look at the 5 centroids that the algorithm found. So like I said, centroids are actually the center of a cluster, right? And in this case, we have like 5 clusters, right? So we have like 5 centroids. So these are the dimension of the cluster of the centroids where they are currently. So what happens is whenever you have like a new instance and you want the instance to fit into the clusters, it looks at the one closest to it, and then it automatically goes and be part of that particular cluster. Okay, so looking at this diagram, we can see like we have like lots of polygons, and a polygon is a shape that is fully closed. So you can see we have 1, 2, 3, 4, 5. We have like 5 polygons here. Now, these polygons are partitioned using the addition boundary. So we can see the addition boundary here and also here. Right now, each polygon also contains one generating point, right, known as the centroid. So we can also see the x, 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 x. Yeah, and that in that polygon, all points, all the instances in that particular polygon has the points like closer to the centroid, which is the generating point. Now, this is referred to as Voronoi tessellation, right? Because in Voronoi tessellation, there is like a center point for polygons, so you can easily see generating points, which is noted by X here. Also, looking closely, you realize that some instances are close to the decision boundary, which is this line here. So these instances might be wrongly classified. We can't even say that they are rightly classified because they fall in between probably 2 different polygons or 2 different clusters, and they might be misclassified. So now, because of this, right, because of each clusters have different diameters, right? So if you look at this place, you can see that each of these clusters have like different diameters, and all the algorithm care about is the distance of an instance to the centroid. So it's not bothered about any other metric to classify it. So this is known as hard clustering, when all we are concerned about is just the distance of an instance to the centroid. That's the distance of an instance. That's like a variable here, or one of these things to the centroid. Now, so that each of the items are assigned to just only one cluster. So you can see here that all these items are assigned to just one cluster. It's not more than one. So it's not so reliable for instances that fall in between the decision boundary. So another approach we can use is soft clustering. And what is soft clustering? So soft clustering actually uses similarity score, and that creates a function that quantifies the relatedness between 2 different clusters or more than 2 different clusters. So rather than assigning an instance to a cluster, it tells us about the probability of that instance being part of the cluster. So if you can see here, you can see for 5, you have for this particular cluster, this is the probability, this is the second, this is for the second cluster, the third, fourth, fifth. So it assigns like a probability value, or a value that tells the closeness of that particular instance to that cluster. And the transform function measures the similarity score, as you can see. So how does K-means clustering algorithm work? So there are 4 major steps. It places the centroids randomly, and by default, we're not giving the centroids, neither are we giving the labels, but it places the centroids randomly. It labels the instances, it updates the centroids, and it repeats until centroids stop moving. So although it places the centroids randomly, remember that for K-means, we have to define the clusters by ourselves. And if you want to get a centroid for a particular cluster, that's like the mean of the instances in that particular cluster. Right, so before placing any centroid randomly, there must be a cluster that, fine, we are dealing with 5 clusters, then you can start placing centroids randomly. So the next step is this. Let me see. Now, sometimes the process converges to the wrong solution, right? Because it is initializing the centroid randomly. Like this is one initialization here, this is another one here, and it doesn't look like these are optimal solutions. So one way we can have better centroid initialization is by setting the numpy hyperparameter to another clustering algorithm array. So if you've run an array of, if we've run a clustering algorithm previously, we can easily use that centroid cluster, that the centroid values right, in the new task we are performing. And we can always run the algorithm multiple times and choose the best value, the best solution. So by default, the number of times we can run the algorithm is 10 times. So when the set init hyperparameter is not 1, it is 10. That's the default. So we run it 10 times and then choose the best. Also, while k-means starts with allocating cluster centers randomly and then looks for the better solution, k-means plus plus starts with allocating one cluster center randomly and then searches for other centers given the first one, right? And also accelerated k-means algorithm, and this solves it in form of a triangle inequality. And how does it do this? It determines the lower bound and then calculates the distance between the lower and the upper bound. So it's like having like a triangle, right? And the shortest distance between those 2 points is a straight line that joins the triangle together. Now, performance metrics for k-means algorithm for unsupervised learning. So there are actually two. We have the inertia and we have score. So after training with multiple centroid initializations, how do you know the best one? You can make use of either inertia, performance metrics, or score. And inertia is like the mean squared distance between each distance and the closest centroid. So the metric is available using .inertia function, which is available in the k-means class. And the smaller the inertia, the better the initialization. So if you look at this example, the one with the score that has the value of 211.59 is a lot better in value than 223.3. However, we can make use of score performance metric, which is negative of the negative inertia. And the reason why we're making it negative is because you can't say that a model is not performing rightly and then it should not have like a higher score. So that's why we're making it negative. So if 211 is actually better than 223, when you have the negative of 211 and 223, 211 becomes like higher, right, and better than 223. So now a bit of mini batch k-means algorithm. So rather than allocating clusters centers randomly for a whole data set at once, why not group them into different batches and just remove the centroids just slightly at each iteration, right? So this is a very good approach because it saves so much time and speeds up the process by a factor of 3 or so. And also it is possible that we cluster like really large data sets. If we are using k-means for really large data set, it takes a lot of time. So if you look at the diagram here, on the right-hand side, we can see k-means is red, mini batch is blue, and you see that mini batch is a lot faster when it comes to training time than k-means, especially when you are making use of like a large database set. And looking at the left-hand side, now comparing the inertia, mini batch actually becomes worse as number of clusters increases, right? Although their training time is faster, like we discussed. Now, finding the number of clusters. Now, this is a very big problem, right? Because even if you actually want to, even if you want to follow the format, place centroids randomly, you still need to find clusters. How many clusters do we need? How many clusters do I need for my project or the task I'm working on? And all of these are really nice to know when we know the number of clusters, right? So we can only place centroids randomly when we know that, fine, I'm dealing with like 4 clusters, I'm dealing with 5 clusters. So for instance, looking at this diagram here, we have 3, we have 8. So this one looks like it should be 1, but then it's 2. So because we have like more clusters, so bad choices for clusters just makes the whole results really, really incorrect and misclassified. So, and also you might think, fine, can we just make use of the low inertia? Because I said when you have like low inertia, that means when you're testing it multiple times, when I mentioned 10 times, when you have low inertia, that means the particular instance that was calculated is right. So breaking news, low inertia doesn't guarantee you find the right number of clusters, because the more you increase the cluster size, the lower the inertia becomes. So if you have 5 is 6 is lower than 5. So if you really want to get a low inertia, you can use 10 clusters, and then that's not still the best result. So there are various ways we can actually get the number of clusters. One of the ways we can do this is the coarse approach, right? So we plot the inertia as a function with number of clusters, right? And there is an inflection point called the elbow. There's an inflection point called the elbow. Now, taking a look at this particular diagram, yes, this is the inertia, this is the cluster. We can see that at point 4, it looks like 4 is actually, there is that inflection point that actually goes down, and then 5 still goes down a bit here. But this 4 looks like the breaking point or the inflection point. So we might actually be tempted to choose 4. 4 might actually give us the answer, but it's not the most appropriate answer for the data set that we are considering, given the inertia and number of clusters that we have. So we find the inertia value for when we have 2 clusters, 3 clusters. So we can see that the more we increase the cluster, right, the smaller the inertia value becomes. So we can't even use inertia as, to get the number of clusters. So if you look at this breaking point here, fine, let's look at this point. Maybe this is when this is right amount of cluster. So this approach generally is not really the best, right? Because although it is less computationally expensive because you don't do so many calculations, but yet it's not the best. So another approach that can actually give us a better result is the silhouette score. So computing the silhouette score for each of the labels. So this is what we have, right? So we have the silhouette score on the x-axis, on the y-axis, and then we have the number of clusters on the x-axis. So we can see again that 4 gives the best result in terms of silhouette score. I had the silhouette score, the much appealing the results is. So 4 gives the highest silhouette score, close to 0.7, but not 0.7. Yeah, 5 also is good. 5 looks really nice. It's not as low as 2, 3. These ones are really low. 6, 7, 8 are also very low. Silhouette score is better because you can see 4 and 5 actually standing out. But looking at this one here, you might be deceived that fine, 4 is down, 5 is down, 6 is down, 7 is down. You might not know the right one to choose. So silhouette score is a lot better than the coarse approach where you plot the inertia with the number of clusters. But still, we are still confused. We are still confused. Should we go with 4 or should we go with 5? So one thing we can do is we can plot the silhouette diagram. And this is like a very nice approach, right? Because you'd see the number of clusters on the y-axis, and then you see you'll see the clusters instances on the y-axis, and then you see the silhouette coefficient on the x-axis. So in this particular diagram, we can see that for when x equals to 3, we have 0, 1, 2, 3 clusters. X equals to 4, 0, 1, 2, 3, 4. And this line represents the silhouette score. So this is the coefficient. Let me remove this. Sorry. What's this? Okay, this is the coefficient here. So for x equals to 5, x equals to 6, x equals to 4. But now, how can the previous approach we've been using, they've been telling us that 4 is the best, or 5. So we are now stuck with 4 or 5. But looking at this diagram closely, we can see that 5 is even much more appreciated because it cuts through all the clusters. So looking at 4, it doesn't really cover this 2 as much as this 5 covers all of them. So 5 is the best cluster that we can use for the particular clustering task that we are working with. So limit of KNN. Now, despite many advantages of KNN, it's very fast and all of that. KNN is not perfect, right? So as we saw, it's necessary that you run the algorithm several times, 10 times by default, if you want to actually get the best results. And also, number of clusters is needed. They don't give you the number of clusters. You have to still probably use silhouette coefficient, silhouette diagram to get the appropriate number of clusters. Sometimes you might be wrong if the data set is not linear. And yes, it doesn't behave well when clusters are varying sizes. So this is what I mean by varying sizes is if you have like different densities or different orientations of the data. So now I mentioned data is linear. So if data is not linear, if data has like different densities or different orientation. So in the next diagram, we can see that this particular data set is is more centric in the middle of the plot. So it doesn't really tell us like, fine, this it can't really define the center blob or the center properly. So this is one of the limit of KNN. Now there are really awesome applications of clustering algorithm, one of which is image segmentation. So there are two basic types of segmentation. We have the semantic and we have the instance. So what the semantic does is the same objects are assigned the same pixel value. That's a wrong explanation. So the same object, right? If a particular, now these are different persons. So since it has like a pixel value, so they belong to the same segment. That's for instance. That's for semantic. And for instance, it classifies them differently. So what we are doing now is color segmentation, which is like a type of semantic, right? So it takes the particular color and looks through the image and assigns that color the same segments. So how can we do this? So the image we are making use of is a ladybug image. Yeah. So this is the path to the image. We read the image, and this is the image shape, the height, the width, and the color channel, which is 3. Right. And then we reshape the image. Yeah, and we experiment using 8 clusters. We are defining our clusters. We're not using silhouette coefficient or silhouette diagram to get our clusters. Right. And also we segment the image based on the number of labels. So this number of labels actually is the number of clusters. Because if you have like 8 clusters, definitely you have like 8 labels there. And you plot the image. So let's see. So looking at this diagram, we can see that when we iterate, from 10, we can see the original image when it was plotted. We can see 10, we can see 8 colors, 6, 4, and 2. And you realize that when we get to 2, it just shows just 2, that's green and yellow. And when it gets to 6, it tries to show the color channel that we actually want to see. So this is a very nice way of actually, segmenting images to different colors. And the reason why in 2 we can't see probably the red, I think the red stuff on top of the flower is
So
because
that's the ladybug.
okay, the ladybug, yeah, top of the flower is because it fails to dedicate a cluster to it. So because we have like just 2 colors, it just removes the bug and we can just have the yellow and the green. Yeah, so now clustering for preprocessing. Now this is really nice. And the data set we're making use of here is the MNIST data set. That's the DDT data set. So let's try and preprocess the data without, let's run the data normally without even making use of any K-means algorithm. So when we do that, we get 96.9. So this is our baseline accuracy. So now let's try and use K-means for the task. So what we do is we create a pipeline and we specify number of clusters. So we know that there are 10 different digits. In the MNIST data set, we have from 0 to 9. That's 10 different digits. We can choose to assign 10 as number of clusters, but let's, these digits might not really be the same all through. So let's assign 50 and see what the algorithm will do. So after fitting it, we try and get our results. So we can see that it's a lot better than actually using it without actually preprocessing the data. So that's like 2.2% better than the 96 that we have here, 96.8, 97.7, yeah, it's a bit. So we reduce the error rate from 3.1, that's 96.6, to 97.7, that's 2.2. Yeah, so another thing is we just, for the number of clusters here, we just, guess randomly, let's try 50, let's see what 50, and when we tried 50, we had like a better result. So we can, make use of grid search to actually learn and calculate the optimum number of clusters for us. So using grid search here, using grid search, we can see that we specified a range from 2 to 100, and definitely grid search chose from 2 to 99. Yeah. So yeah, and then grid search chose 99 is the best number of clusters because like the highest. So if we try, let's say, increasing the number of clusters here, the number of clusters, yes, it might actually choose the highest. If you can try this with 150, it might 150 that might actually be the highest number of clusters and might get a significant accuracy boost. So when we use grid search to iterate over different clusters, and after the iteration, it's finally decided that fine, 99 is the best, it gives the best results. So we can experiment with, let's say, higher numbers, maybe 200, and see what that gives us. So another interesting use of clustering is semi-supervised learning. Yeah, so we have labeled instances, we have unlabeled instances. So let's train a logistic regression model on a sample of 50 labeled instances from a GG data set. So rather than using the whole 100, we're making use of 50 labeled instances. And when we do that, definitely when you are training on less number of data sets, you don't expect to have like a really large high accuracy. So after doing that, we have 83.3%. That's the score of the model. So let's now make use of clustering for semi-supervised learning. So what are we going to do? So for each of these instances, we are choosing a particular representative that represents that particular instance. So we have 50 labeled instances now. And instead of randomly choosing the images that represents it, so we'll choose a particular image that represents each of the clusters. So if you have 50 clusters, right? So we are not using all the instances in that cluster. We are choosing just one. So when we do that, this is what we get as the accuracy, the performance score, which is higher than 3.3. So this is like a diagram that shows representative images that we're using. So rather than making use of all the images in that cluster, we are choosing just one of the image and we are using that to represent that cluster. And we're now using it to make our conclusion. So now let's now try propagating the labels on all of the instances in the clusters formed. So when we do this, we realize that when we do this, we realize that the result is 93.3. And the reason why we have this, it's not so high compared to 92 here. It's not so high compared to 92 because when we actually use a representative instance or a label for that particular cluster, we get 92, which is like a big improvement from 83.3. But when we are now trying to label all the instances, we have 93.3. And the reason being that some of the instances that were labeled might have been wrong from the centroid. So rather than actually labeling all the instances in that particular cluster, let's try and label just 20%, the ones that are 20% close to the centroid. So that's what they did here. And we tried labeling for 20% and we have like 94, which is a lot better than 93.3, from 92 to 94. So we are making use of the instances 20% to the centroid, not just all instances. So if you remember clearly, we also discussed decision boundary. So it's like actually labeling all the instances, and some of these instances are close to decision boundary. So rather than doing that, we just need the ones very close to the centroid, 20% from the centroid. And when we do that, we achieve a score of 94%. Yeah, so inference, so we just 50 labeled instances, only 5 examples per class on an average. We got 94.0 accuracy. So 5 means 20%. Yes. So, we used 1 initially, then we tried to label all of them, then we now used 5. So, which is pretty close to the performance of the logistic regression. So if you're making use of fully labeled on all the data sets, it's 96.9. But we're not using all the data sets here. Now, active learning. To continue improving your model and your training set, the next step could be a few rounds of active learning. So how do we do this? The model is trained on labeled instances gathered so far, and these instances are now then used to make predictions. So the instances for which the model is uncertain is given to like an expert to label, right? After the expert has labeled the instance, the process is iterated again until experts are no longer required. So this method of active learning is also known as uncertainty sampling, where you need an expert to actually help in labeling the data, the predictions that had like the least probability of occurring. So it's like the highest error or something like that. So when the expert actually says, fine, this is not meant to be here, this is meant to be here, then the process is repeated again. The model is trained again on the labeled instances, the ones that add and these labeled instances, we now include the expert's opinion to it, and we make predictions again on all unlabeled instances. Yeah, so DBSCAN in a nutshell. So I mentioned that there are two major types of clustering algorithm. We have K-means and then we have DBSCAN. DBSCAN is also known as density-based spatial clustering of applications with noise, and it defines clusters as continuous region of identity. It's used when clusters have arbitrary shape, that's random shape, and used when clusters contain a lot of noise. So I downloaded an image here from the internet. So we can see in this particular image, there are two clusters. We have the yellow and then we have the blue. And also, like I said, DBSCAN has the ability to detect noise, so you can see that all these ones that are black, they are noises. If we're making use of K-means might have said this belongs to cluster 1, this belongs to cluster 2. So DBSCAN has the ability to actually detect noise in the data set and outliers. And the next diagram shows that, compares this with K-means. So if we are dealing with K-means can't, if you are looking at data sets, they have to be linear. You can't probably say one in one cluster belongs to the other cluster and they are in two different places. And they are like in the same, they have to be in two different places. But with DBSCAN, they can be in two different places. But with K-means, I'm contradicting myself. With DBSCAN, right, you can't, with K-means rather, you can't say you have cluster 1 here and then you have cluster 1 here. They have to be in the same place, which we have in K-means. But DBSCAN can actually, go around based on how dense the data set is. And also looking at the other example down at the bottom, you can see that for K-means, the instances closer to the green are labeled as green. But for DBSCAN, if the instances are actually yellow, it tells you that it's yellow. It doesn't just say fine because you are closer to the this one, we now have to label you as blue. We can label you as yellow because you belong to this one. So this is DBSCAN in a nutshell. And there are two parameters required for DBSCAN algorithm. We have the epsilon and we have the mini point. So for the epsilon, we define the neighborhood around the data point, and for the minimum point, we define the minimum number of neighbors required for data point. So all these 1, 2, 3, like all these for this particular yellow that we have down here. So all these points are like neighborhood. So if you have minimum points, so we define the minimum number of points in a radius. That's the epsilon. Epsilon defines like the size of the radius. So if we have this size or lesser than this size, let's call it a cluster. That's what epsilon does. It defines fine. Let's say clusters are 10 centimeter, something like that. And it can be 10, it can be 9, it can be 8, but it should not exceed 10. In that kind of idea. Minimum points, how many points should we have there is the minimum. You can't say you have a cluster of 10 centimeter and then you have just 3 points there. If the plan is to probably have the minimum point that I should have in a cluster is 15, then you put 15 there. So this is explanation, better. So if the distance between 2 points is lower or equal to epsilon, then they are considered as neighbors, like I said. So if it's 10 or below, they are neighbors. But if it's above 10, no, they are not neighbors. So if epsilon value is chosen, that if the epsilon value that is chosen is too small, then large part of the data set will be considered as outliers. So like this other part here that we have outliers. So if the value of this epsilon is too small, then it's see all this part are outliers. So for instance, if the value for epsilon was larger here, it will have picked all these values and probably made them blue. So that's about that. And if it's chosen, if it is chosen very large, yeah. So one way to find the epsilon value is by making use of the k-distance graph. Yeah, so this is like a practical example. So we can see here that in the left-hand side, epsilon value of 0.05, minimum sample of 5. The value for epsilon is too small, very small. It's like saying After every 1 centimeter, that is a cluster. That's why it looks like it. But when we increase the value of epsilon, right, let's say 0.20, fine. So that's why it's, it's a lot better. So you have to always, interchange this and make it work. And if you want to determine your epsilon value, you can make use of k-distance graph. So other types of clustering, we have agglomerative clustering, right, which is like from bottom up. So what do? You merge, you start from like one cluster and you merge these clusters until the number of desired clusters are actually achieved. And if you want to implement it, you make use of the agglomerative clustering class and tune the n cluster sets as an estimate of the number of clusters in data sets. And then we have batch. So batch generally deals with available memory and time constraints. So its full meaning is balanced, iterative, reducing and clustering using hierarchies. It makes use of hierarchies and dynamically clusters incoming multidimensional metric data points to try to produce the best quality within the available resources. That's for Birch. And affinity propagation is more like a voting process where each instance in a cluster communicates between themselves and they're like, fine, I think that guy should come and join us and be part of our cluster. So voting system, instances vote for similar instances to be their representative, takes inputs measure of similarity between points, revalue, and I think that's all I have for today. So the other parts, the other algorithms that we have mean spectra, and we have Gaussian mixture. So Gaussian mixture is what I'll start with next week.
Oh, that's good.
Awesome, Toby. This is very, very good. Any comments, reactions from anyone else?
I actually had a question for Dr. Kuchaya. So I was wondering if we know of any semi-supervised learning in radiology, or is it always, you got to label and then, like, do you know any instances where they like label them a little bit and then, the algorithm went along with it to propagate?
So radiology, I'm assuming you're asking specifically about the medical imaging, right?
I guess so, yeah.
Yeah, because so that, the thing about that's the challenge about this is a convoluted answer to your question, but if you see the answers that we see, if you think about like mammograms, right, and you see like what Toby is presenting, it's like we just have these grayscale images that are very difficult to show the difference for a true like unsupervised learning where you're doing data discovery. And right now when I was reading through this chapter and also re-listening to the presentation, I wondered if we could even find anything interesting if we just put x-rays and start to see would they localize on something like support device, because I think you need a little bit more contrast to show in the boundaries, but I don't know. The thing what people have done mainly has been semi-supervised learning, like you said, where you label a few things, then you propagate it to other people, and then you have this not active learning but active labeling, right? So you run your model and then I come back and say, okay, you label these chest x-rays, can you look at the model predictions and say if they're okay and not okay, and then move that way. So I do believe that this is super powerful, one, because it can even just be done from, I liked a lot. So every time we do a classification task, for example, right now there's an ongoing Kaggle challenge for predicting if the endotracheal tube or central line is normal or abnormal place. So that's a classification task, right? It's a multi-class problem. The winning models usually are an ensemble. So it was interesting to see how this scikit-learn is like, oh, could you show me like a cluster? So I wondered, theoretically, I haven't tried it, if you could even just download that, and maybe Chima may try this, but because he's working on these challenges, and Zach too, is to say, why don't we use a clustering and see what are the clusters that come up from this data set, and then you build another model, in that pipeline approach to see if you get better performance or not. So I think when I think of this unsupervised learning it still requires a lot of, like, you have to be presented with the data and then to decide, oh, why do you think this is one cluster versus another cluster? And we should experiment with it more, but it's mainly been used for labeling.
Cool.
Chima, any questions, reactions to this?
No, I especially like the explanation of the other, towards I think the 52 to 55, those models, I like those ones. They help me grasp it very well.
Okay. Zach, any reactions to this topic?
Yeah, I mean, when I read this chapter in the book, I was kind of struggling to see the difference between what k-means and DBSCAN aside from the outliers, but the graph in 48 really helped me visualize what DBSCAN does versus what k-means does.
Mm-hmm. And remember, DBSCAN doesn't have a prediction, right? You just use that process to get to something else, right?
Yeah.
Remember this, right? It doesn't have a probability, and on the code they show how you can use like the DBSCAN and then use some of the stuff there to move to something else. But okay.
Right.
So I know Toby, over the holidays ran his own study group. I mean, he's even stepped out even higher. That's a message for you, Chima, but no, I'm kidding. But I mean, you can just see there's just so much clarity in your explanations. And I was wondering, how far did you get with the other reading group? How are they doing? Did you finish the whole book?
No, so I actually stopped. I'm thinking of probably stopping the group now.
Yeah, because you're busy.
Yeah,
How far did they get?
So we stopped at chapter 4.
Okay, I mean, if they watch the videos and can catch up, they can join us. I don't mind. Okay? Yeah. Okay. Why don't you send them the YouTube link and they're welcome to join. Okay. Okay. So we'll continue. If there are no other sort of comments, I just want to highlight a few things people have been posting on the channel, which is like some experiments. One of the things that I've said that people have different sort of expertise and, will have different pathways, but I do believe that I saw Sina could sit through technical talk and be like, oh, I understand what they're saying, so I take that to be a big win. So I know that after next week, we will, Toby posted 160 data science and machine learning problems. I try and post a lot of the things there. Please share the PowerPoints. I like the PowerPoints because it's easy. You can go back to them and be like, oh, what was going on with this topic? And you can kind of review it. And then I think once Toby comes to the end of next week, Nazanin will be taking us through chapter 10, which is the neural networks. Okay, finally we get to neural networks. And then I know I haven't forgotten, Chima, where you are reviewing that book, which is the feature engineering.
Yes.
Super important. Now those skills are super important if you get them, someone like Chino or myself, because if you can do feature engineering, you can understand what the model is doing and you can design better projects, and other people can do the writing of the code. Okay. Mm-hmm. Okay. So please work on that, Chima. What we may end up doing is that may be a presentation like during one of the lab meetings.
Okay.
Yeah.
100% would love to do that.
Okay. 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 Well, see you next week. Thank you. Bye.
Bye.
Thank you.
We want to see a new picture, Toby, next time. Behind there, not just the eye. Okay. Bye.